All right, this is Algebra 1, Lesson 11.7. We're going to look at adding and subtracting radical expressions. Let's start with our warm-up. So we need to simplify the expression. So basically that means we're going to combine anything that's a like term. Remember, we can only combine things that have the same variable and the same power on that variable. So this 14x and this x can be combined, which makes 15x. Remember, you're adding the numbers that are out in front. And then this 15y and this negative 12y can be combined. 15 minus 12 makes 3, a positive 3, and we need to keep the y with it. Okay, on this next one, so if you notice, they've all got x and y, and they all have the same powers on that x and y. So we're going to add 9 and 2, because it's a plus sign, and then subtract 8. 9 plus 2 is 11, and then 11 minus 8 is 3. But we need to attach that common variable on too. All right, for the next one, you want to distribute first. So we get negative 3a minus 3b. Then we get plus 10. And then when we multiply a 5 through, we're going to get 5 times 2, which is 10. And then 10 divided by 5 is 2 and b. Or you could just think of it as this 5 cancels with this 5. But you still have to multiply it to this one. Now we can combine only our b values. So we're going to keep the negative 3a. That doesn't combine with anything. The negative 3 and the positive 2b make a negative 1b. And then we have plus 10. Okay? So a little bit more of our warm-up. It wants us to simplify the radicals. So we're looking to see if anything, what's the greatest perfect square that goes into it. So on the first one, if you tried all the numbers, the biggest one that goes into 96 is 16. So we can rewrite that as 16 and 6. And then the square root of 16 is 4, and there's no perfect square root of 6, so we leave that under the radical. Okay, on this next one, remember there's a 2 out here, so we want to see how many times does 2 go into this exponent. So 2 goes into 9 4 times, so we can take out an x to the 4th, but there's a remainder, okay, inside of an x, because 2 times 4 is 8, and so there's 1 left over. And then 2 goes into 10 5 times, so we can pull out 5 y's with no remainders. So we have to keep that x, that single x, under the radical. All right, with the last one, you're going to want to simplify the 72 and the 81. 9 goes into 81 9 times, and 9 goes into 72 8 times. So we can rewrite that. Radical 8 times radical a to the 5th over radical 9. And then we can rewrite radical 8 as radical 4 times radical 2 times square root of a to the 5th, and then the square root of 9. Now I'm going to simplify everything that I possibly can. I know that this 4 simplifies to a 2. I know that I can divide 2 into that 5 2 times, so I can pull out 2 a's. And then under the radical, I'm going to have this 2 left, and then one of these a's left. And then down below, the square root of 9 is 3. Okay, so again, we just combine everything under the radical that doesn't pull out. So in this lesson, we're going to look at adding and subtracting radical expressions, and you're going to hear this term like radicals. Square root expressions with the same radicand are examples of like radicals. So remember, a radicand is what's under the radical sign. So for example, 2 times radical 5 and 2 and 4 times radical 5, those are like radicals because they both have 5 under the radical. In this one, they both have an x under the radical. In this one, they have the 4 to the t under the radical, so those are all like radicals. These are unlike radicals. They don't have the same thing underneath the radical sign. So like radicals have to have the same radicand, meaning the same thing under the radicals. With radical expressions, we can combine them by adding or subtracting. You can use the distributive property to show how this is done. So for example, 2 times radical 5 and 4 times radical 5, what you can do is you could pull out the 2 and the 4, and if you added those together, it would be 6, and then you keep the radical 5 next to it. It's kind of similar to, and I'm going to talk about, it's kind of like a variable. You kind of, when it has the same radical, you treat it like a variable. So on this next one, for example, if I have 6 radical x minus 2 radical x, I would subtract the 6 and the 2, and that would be 4, and I would keep the radical x. Nothing that you can combine like radicals, or sorry, notice that you can combine like radicals by adding or subtracting the numbers that are out in front, and you keep the radicals the same. Like I said, it's kind of like combining like terms. So if I had 2x and 4x, I would add the 2 and the 4 to make 6x. And it's very similar. You just keep what's in front, you add those together if that's what it says to do, and then you keep the same radical. So let's try some examples. So if I have 9 radical 3 minus 4 radical 3, I would take the 9 minus the 4, and that would be 5, and then I keep the radical 3 next to it. On this next one, we have to look, is what's under the radical the same? Do I have the same? No, I don't. I have an x and I have a y. So those can't be added. They're already simplified, so you just keep them as they are. Okay, let's try these next ones. So if I have radical m minus 7 radical m, what you want to think, there's a 1 out in front here. So that's taking 1 minus 7. We already have the same radical. They both have m's underneath. 1 minus 7 is a negative 6, and then we keep the radical. Okay? On this next one, only this one and this one are like radicals. So because it's a positive 9 and a 2, that becomes a positive 11, and we keep what's next to it, the radical. And then we just keep the 2 radical y, because it can't be combined, since it's not a like radical. Sometimes radicals don't seem like they are like until you simplify them. So you have to simplify all your radicals before you can decide if it's a like radical. So let me show you. All right, so if we look, these ones don't look like they're like radicals right now. However, if I simplify them, I can show that they actually are. So we can split 45 up into radical 9 and radical 5, and then we can split this up into radical 4 times radical 5. Well, the square root of 9 is 3, and I don't have anything to do with the 5. The square root of 4 is 2, so now I have 3 radical 5 minus 2 radical 5. 3 minus 2 is 1, and then I have times radical 5. And you could write it as just radical 5. You could either write it this way or this way, because you can put the 1 in front, it doesn't matter. So again, you couldn't do anything until you made them like radicals. So we're going to check on this one. Okay, they don't look like they're like terms yet, but let's see. So the biggest perfect square that goes into 75 is 25, and it goes into it 3 times. With 50, the biggest perfect square is also 25, but it only goes in 2 times. Now, if we take the square root of 25, that's 5, and what happens is it gets multiplied by whatever was out in front. Same thing on this next one. The square root of 25 is 5. We can't do the square root of 2. So now we have to do 9 times 5, which is 45 radical 5, plus this one, which becomes 10 radical 2. Now, we don't have the same radicand, so we can't combine these any further, but you should leave them in the simplified form. You can't just say, oh, this is your final answer. You want to get them into the most simplified form. We just can't add them any further. Let's try this one. Okay, if you notice, they all have a y underneath, but the numbers are different. So we have to check if we can simplify the numbers. So the square root of 75, we can rewrite as the square root of 25 times the square root of 3y, because I got to keep that y there, minus 2 times the square root of 9 times the square root of 3y, and then plus the square root. I know 16 goes into 48 3 times. So now I have the square root of 25, so I have 5 radical 3y, minus the square root of 9 is 3, but I have to multiply it by this 2, which makes 6. Then I have the square root of 16 is 4 with the radical 3y next to it. So I've got 5 minus 6 plus 4. If I combine all those, I get 3 radical 3y. Just remember, when you write a radicand as a product, you want to, like I did up here, you want to make at least one of them a perfect square. And you want it to be the biggest perfect square that you can. So for example, we knew 25 was the biggest perfect square in that one, 9 was the biggest perfect square here, and 16 was the biggest perfect square there. All right, we've got one last example to do. It gives us a triangle, and it wants us to find the perimeter of the triangle and give our answer as a radical expression in its most simple form. So you have to know what a perimeter is. So perimeter, remember, is what's going along the outside. It's not the area. The perimeter is just the outside. So to get the perimeter, that means we would add all the side lengths up. So let's write that out. So we'd write 3 radical 20 plus 13 radical 5 plus 10. And we should put our units, but I'm going to leave those until the very end. All right, we need to see if we can get 3 radical 20 any simpler. So we can rewrite that as 3 radical 4 times radical 5. And I'm going to rewrite this. We can't simplify radical 5 anymore. The square root of 4 we know becomes 2, which multiplies by the 3. So I have 6 radical 5 plus 13 radical 5 plus 10. Now I can combine these two terms. So I get 19 radical 5. I can't add the 10 in because it is not a like radical. It doesn't have a radical 5 after it. So you have to just keep it. And what you always need on your word problems is units, so millimeters in this case. So this is the most simplified perimeter of this triangle. So just to review, you cannot add radicals unless they are like radicals. That means they have the same thing under the radical sign. Okay? Sometimes you have to simplify them first to check if they are like radicals. And we'll do some more practice with it in class.